So let's start. Okay. So, I think last time we were what were we discussing last time? So I introduced you how early, basically the combining the threshold dynamics idea we learned in the population dynamics and how the properties of the Ornstein-Uhlenbeck process, right? Those two can be combined to devise what we call early warning signals. That's what we did last time. So we learned one application. So I will, in the next assignment, what I will do, I was thinking of doing a different kind of assignment this time. So maybe I will do the following. I will ask you to read a couple of papers and comment on those papers. So that will be the kind of assignment this time. Okay. And there will be some empirical papers, some theory papers, and so on and so forth. But just tell me, I want to make sure the assignment is realistically long. I don't want it to be very, very long. Okay. So, so this is the format I was thinking. Okay. So I was thinking of, the following sort of questions. So there is actually a paper in 1984, okay, by somebody named Fissel, which uses these ideas, of autocorrelation, time and related ideas. Okay. And then there is another paper in 2007, okay, by another set of authors that does something very similar. Okay. Okay. Now this is a paper in Oikos. This is the paper in American Naturalist. This is one pair of papers. And there is a second pair of papers. So both of these are mostly theoretical work. Now there is another set of papers which are basically empirical papers that test the idea of this early warning signals in biological systems. So there is a paper that uses Drake et al. So in 2010, they used Daphnia as a model system in their experiments. Okay, and then there is a paper okay, I think around the same time maybe. They use yeast as a model system. These are both experimental papers. Okay, so let's call them experimental empirical papers. Then there are also field data. There are about 3 papers. Carpenter et al. 2010. This is from Lakes. Okay. And then there is a paper. Okay. I think this is again Lake, but they use some diatom data. Okay. But it's still about Lake regime shifts. Okay. And then there is a paper that uses semi-arid grasslets. In fact, I think arid grasslets, if I'm right. So you can see there is diversity of papers available. So what I was thinking was, asking some basic questions using sort of, these papers as reading. I want to know what's a realistic, reading that you can do, given that, and especially I'm thinking from the UG students' point of view. What would be a realistic paper that you can do? Do you think one pair of papers is, I'm hoping that at least you will be able to read 2 papers. Is it reasonable? But do you think you can also manage maybe 4 papers, or 4 will be too much? What do you think? Can you please send me some
Pair sounds fine, but 4 might be
too much.
Yeah.
Okay. So maybe what I can do then is, so one possibility might be that different students choose different pairs. You are entirely at your sort of you know, your discretion to choose whatever you like. Okay. So maybe in fact I will remove this paper because it's why two papers on lakes. Okay. One lake and one. So this is the field studies. So maybe two, sort of, theory and simulations paper. This is a pair, and then this is another pair. This is another pair. Okay, and maybe there is a review article that maybe I would encourage everybody to read. Okay, at least some parts of it. It's a fairly well written paper. You know all the mathematics, all the biology, all the ecology to understand at least half of the paper. Okay, which is what is relevant to us. Okay, so maybe what I can do is I can ask people to read some section of this, and then you can choose any of these three pairs, and then for each pair I would give some set of questions. Is that fine? And then maybe what I can also do is that I can ask you to make a small presentation based on your assignment. Would that be a good idea? Maybe the assignment could be entirely presentation, not any no written submission. How about that? Would that be okay? What do you think of that possibility? How many creating students? About 17 to 18 students, 20 students, including the people who have been regularly auditing, right? So how do we do this though? 20 people presenting will take too long.
So we'll also be presenting the final project, right? So
that's a different thing. The final project is a very different thing. Anyway.
Yeah, so I think like two presentations will be a little too much work.
Too much?
Yeah.
No, I was thinking of really short presentation, like 5 minutes. Or do you prefer written submission? Is it what you prefer? Written submission is also fine. So maybe then I'll stick to the following. So the assignment 3 will be as follows. Basically, there will be 3 options. You can choose 3 of these pairs of papers, and then for each of the pair, I will ask you some questions and ask you to comment on them. And everybody will be asked to read first half of this paper. Is that fine then? I will have roughly for another 2 to 2.5 weeks from now to finish this. Shall we do it that way? Okay, I understand that presentation also will require a slot.
Hear your voice for the past 30 seconds. Could you repeat what you said?
So the thing is, I was debating the possibility of presentations versus, a regular assignment based on this. That's Sharad said that the presentation might be too much because you also have a project presentation in there. Is that what the consensus opinion is? Is that what everybody thinks? Yeah, I mean, I think let's not worry about the presentation. Okay, so let me just do a regular assignment, but I will ask you to read papers in this round. Okay, so I have given you some idea of what these, what the kind of papers will be. I will just write that up and upload by weekend. Okay, and okay, maybe I will give you some hints to make sure you don't spend immense amount of time just reading through the paper. Okay, so when you read the paper, let me just give you some general sort of tips. General tips for reading papers. Okay. Now the review articles you may have to read the section I say completely, but in general, when you read any paper, of course you will read the title and see if it makes sense. What does it convey, right? And then of course you will read the abstract. Any good paper will have a good abstract, and the abstract clearly will state the context as well as the result they have found. Okay, so now based on the title and abstract, you must know the claims of the paper. The claims must be clear. Okay, now that's something you must note down at this stage. What are the main claims of the paper? Okay, context you have, since you have the background in this course, since we have spoken, you have the context, so that you must be fairly easy to appreciate. So you will understand the claims of these papers. Okay. Now the next step comes the introduction. So in fact, what I do is the following. I actually don't read the introduction. I just quickly jump to figures. Okay. So check the figure and captions. So again, if the papers are well written, all the figures, without having to must convey the story. Figures together with captions should be able to convey the story without you having to read anything else. Okay, now that's not always possible. I fully understand. Sometimes it's also driven by journal styles. Some journals insist that the captions are actually very, very boring. So in such cases, by reading captions, you actually will not gain much. Okay, but the papers that I'm suggesting, they're all, I think they're not like that. They're mostly good papers. By actually after the abstract, if you jump across figures and read all the captions, most likely you must also be able to appreciate what has been, what's the main point. So what at this stage, what you should do is there evidence in the figure for the claims made? Okay. Now, you may not find a clear answer to this for two reasons. One, it's a very badly organized paper. You may not find a clear answer. Or it's actually a very rigorously done paper. I know it actually is, you know, what I forgot what I said. There are two possibilities. One is that it's a badly written paper, but a good paper, but a good, well done science study. So in such a case, you will not be clear to you. Of course, other possibilities that it actually is a truly a bad science, badly done. Therefore, the claims are overstated. Okay, so therefore, actually, there's really no evidence inside the. If you really look at the all the results. Okay, so at this stage, you should make a first evaluation of is there evidence for the claims made in the paper. Now you have to now come back to the intro. So now for most standard journals, you read the first para and the last paragraph of the introduction. So these two combinations should tell you the broader context as well as the specific questions they're addressing. So usually this gives a broader context, and the last paragraph often gives you the specific questions of the paper. Okay. And then you go to the discussion section. The first paragraph will now give you summary again of the results in the context of broader stuff. Okay, now this is sort of, this is just skim in this specific order. Okay, by then you might be reasonably convinced about the paper. Okay, now which part of methods you want to dig in, which part of results you want to dig in further will now depend on any doubts you may have. Okay, after that you will sort of look at the methods and results in more detail. Okay. Now, since it's an assignment question, you will eventually have to go through this part also. You cannot fully skip this part. But this strategy of reading in this order, trying to sort of note down a few points as you are going along, this will help you have some clarity and goals in your own reading. Why are you really reading? What are you trying to gain from this? Okay. So of course, only by reading methods and results in detail at the end, you will eventually know the answer to this question. Whether is there really sufficient evidence for that claim, for claims made. Okay. So try to follow this sort of broad strategy. Hopefully that will help you. Is that fine? Any questions? I'm assuming that many of you do already have experience in reading papers, but this might be because it's an assignment where you will have limited time and you also have many other things to do. This is one possible strategy. Any questions?
This is like a general question. So how many assignments should we be expecting throughout the course?
So far we have had 2 assignments, right?
Yeah.
We'll certainly have a 3rd assignment. You may also have a 4th assignment, but not more than that.
Okay. So like it's going to be the best of
we can
like
maybe
that,
take 3 or 4, yeah.
Okay, cool. All right, thanks.
So another question with respect to the project proposals we sent in. when can we like start working on it or like receive confirmation with regards to it?
I thought I responded to all of you, did I not?
No, sir, you haven't to ours.
Did I not respond to you?
Like to our group, yeah, Dipayan, me, Abhipsha, and Uday. Yeah.
I haven't. Okay.
Yeah.
I'm really sorry about that. Maybe I should really have.
We were actually worrying about it, like because everybody else that we know got a response. Yeah.
So it's just a question, case of unfortunately missing one of your emails, the set of emails. So I will do that today. Just remind me once if you don't hear me from by tonight. Okay. Sorry about that. But for everybody else, I think I did respond. Any other questions? Okay, what I would like to have, this might seem like more work for you, but I will assure you it won't be more work for you. End of August, on one of the Fridays, what we will do is I will ask you to make a 5 to 10 minute presentation on the project. Okay. Oh, not August.
It's October.
We can't go back in time, so yeah. We go back, the last week of October, or maybe in the third week of October. Third week might be too soon. The last week will be 15, around 30, right? Yeah. Next week, yeah. So around 29 or 30th of October, the Friday. What I will ask you to each group to do is to make maybe a 10-minute presentation, which basically gives a background. Okay, and exact objectives of your work, exact objectives or questions we are addressing, and the progress made so far. Okay. So if you are 3 members, you can split according to this, your presentation according to this sort of 3 stuff. Make it accessible to everyone. Okay. Especially if the first 2 parts here are not clear, we will not be able to understand this. So these 2 people really should do a very good job. So you must make it very clear what is known, okay, and what you are trying to do. Okay. So so we will tentatively schedule this for basically, yeah, exactly 3 weeks from now. Okay. So this will also be helpful for you because this presentation will be sort of, will help you towards your final presentation. You can sort of, use this again. And I expect that by 3rd week of November, but the latest by the 4th week of November, you will have your final presentation. That we will decide in the beginning of November, or maybe on the day that we do this. Any questions on this? Okay. So in terms of the lab assignments, we have already had 5. Today is the 6th assignment, right? So so I expect, so we will have, so next Friday is a holiday. Okay, so this month we will have 1 more lab assignment, so it will be 7. So in November we may have 2 more, right? Because one of them will be taken away for I think there's again one of the Fridays is a holiday there. A Deepavali holiday will come. So I think we will have 6, 7, maybe 8. I'm not even sure whether we will have 9 lab assignments. Again, there you can assume that one of the lab assignments will not be, will not count. Okay, best of best 6 or 7 of the 8 or 9 will be taken. So this is the lab assignment for today. So yeah, let me give some context to the lab assignment today. So far, we are sort of broadly looking at these kind of stochastic population dynamics, and we have learned about whole process, right? Okay, and remember that when we introduced stochasticity, we spoke of 2 types of stochasticity, right? Additive noise, and the other one was multiplicative noise. So far, this is what we have focused on. We really haven't done much with this. Okay. And how does multiplicative noise arise? Let's take the example of simple logistic model. If we assume that R is a stochastic variable, right? Then the stochastic differential equation arising will be like this. Deterministic part will be same as the previous one, but now we have the stochastic part 2 over n times 1 minus n by k. So now what this means is that the strength of the noise will depend on the current state of the system. This is also called state dependent noise. It does arise in many different forms of biological systems. Okay. Now, what I'm trying to do is the following. So I'll try to, yeah, any questions?
Does this multiplicative noise arise when there are like stochasticity across scale?
Stochasticity across scales. Yes, it does arise when there is stochasticity across scales, but I wonder if that is the only way.
Okay.
That is certainly one way it does arise. Yeah. Why do you think so?
Like it felt like some model in like stochasticity in one level happening because of the plus sign.
Plus sign here.
Yeah, like
So plus sign here has no meaning by the way, because eta, the way we have defined, is always a Gaussian white noise, right? It has both positive and negative values. So yeah, I could have written minus, the equation would be mathematically identical.
yeah. But like the way the noise is given, like it felt similar. Like the deterministic part looks pretty much like the original equation, and the noise as a function, maybe I felt like it could be because of something in lower level.
Yeah, maybe. I mean, it is in this case, the deterministic part happens to be exactly like the previous case, but it doesn't have to be, right?
Okay.
So imagine the harvesting one, the harvesting rate constant h, if that is stochastic, right? Then that term will be different, right? So,
Okay.
so it depends on the in which part of the system does the noise arise. Okay. So this is, yeah. So but you're right that in fact it does turn out that when the noise arises across scales, that's one way multiplicative noise can arise. Another simple way is the noise depends on the state of the system. Now, why does that happen, right? How could that happen? And that one has to think and understand on a case-by-case basis. So for example, what does it mean here, right? Here, what's happening is that if you were to now plot, in this case, the strength of noise on the y-axis, okay. So we can write this in the following way. This is f of n, okay, and this is g of n. So if we were to plot down g of n as a function of n, how will that look like? So g of n time as a function of n is just this term, n into 1 minus n by k, which is basically a quadratic function like this, right? Okay, now what this means is the strength of noise is 0 when the population size is 0. And strength of noise is again 0 when the population size is carrying capacity, whereas it is maximum at k by 2. Okay. Now, why is that the case? Okay. Now, to understand that, you have to see where did you introduce the stochasticity. You introduce stochasticity in the intrinsic growth rate of the system, the per capita growth rate of the system, right? R0 is the per capita growth rate, and there is a fluctuation in that. So basically the stochasticity at the per capita growth rate manifests at the group population level in this form. And maybe it does make sense. When there is nobody in the entire population, there should be no stochasticity, right? Okay, and that explains this limit. and K is the carrying capacity. It's sort of equilibrium limit. Again, at equilibrium, the the per capita growth rate effectively becomes 0 because the births and deaths become equal, right? It doesn't change anymore at that stage. Again, it so happens that if the way you have introduced means that even the stochasticity becomes 0. Now, this is a bit hard to explain, understand. Why should stochasticity in the birth and death at the population level become 0 at the carrying capacity? Now, this becomes a bit hard to explain. Now, the intermediate value is when it's maximum. Okay, now this is also the problem. Sometimes it becomes hard to explain these features, and that's because we have introduced them in an ad hoc way. So, ad hoc introduction of stochasticity does make it sometimes very difficult to sort of explain in terms of the underlying smaller scale processes. Difficult to explain the origin. But sometimes that's one can say it's a phenomenological approach, and we have some empirical reasons to believe this could be true. So this is the way we sort of going back to the introduction of stochasticity. There are these two ways we can introduce stochasticity. Okay, so now do you think whether such a introduction makes something very different? Now we have understood this really well, right? What does additive stochasticity do to the equilibrium? Additive stochasticity basically means that near the equilibrium, system follows a very simple behavior. What was that? So if we had additive stochasticity, implies that system fluctuates around stable equilibrium, and we were able to derive what are the properties of fluctuation and what are the properties of correlations around the equilibrium. Okay, so far for the OU process we have done the following, right? We have calculated the mean, we have calculated the variance, we have calculated the correlations, but what we have not done so far is this. This we have not done. So I will just complete that part today because we haven't done. And to do that fully mathematically is slightly difficult. So I'm just going to motivate how we do that. I'm just going to give you some examples and generalize. So remember when we had random walk? Okay. What's the mean behavior of random walk? It was 0, right? Okay. It was 0. And then what was the equation for probability density function? It was this. Was equal to p by x square. Now do you remember biased random walk? What was the mean behavior? Some p minus q times t. Is that right? So p was the probability of hopping to the right side. Q was the probability of hopping to the right side. Okay. And if you were to think of p minus q as some kind of a representation of speed, the mean value was basically v times t. What was the evolution equation for the probability density function? It was this. Is that correct, everyone? Remember this, right? Where v was basically p minus q divided by delta t, right? That was what the definition of v was. Loosely speaking, heuristically speaking, because this v and this v are not same. Okay. This is what we had. Do all of you remember now? Okay. Now think of the OU process. What is OU process? X dot is equal to minus alpha x x plus beta of t. Okay. Now, what's the mean behavior we found? Start with something like this, right? Okay, I think this is actually a bad way of introducing. Sorry, I think I messed up. Okay, so the right way of thinking about this is not this. Sorry, I think I gave a bad example. Okay, when we write down the equations for this, how was that? So you should think of the equation for random walk in the following way. If you can decompose the equation in terms of a deterministic part and a stochastic part. The idea is, try to see if you can decompose each of these processes into deterministic and stochastic part. In the pure unbiased random walk, there was no deterministic part, right? This was 0. And the stochastic part was that you jump randomly left or right with equal probability. Equal probability jump. Okay. So again, so I'm really sorry about this. I thought this will work, this analogy will work. It didn't. Okay. So let's now again think of the biased random walk. Okay. See, biased random walk can be thought of in the following way. So of course, I'm putting a bit of a jump here to retrofit a few things here. If you were to compose this into a deterministic and stochastic part, what would that be? One can think of the bias part as a deterministic part, right? Bias of p minus q as a deterministic part, and then you can think of the randomness associated with the movement as the stochastic part. Okay, so then this bias term will be p minus q proportional to p minus q, whereas this will be the diffusion part. Okay, so now something I know that we didn't do it this way exactly. Okay, so my analogy is sort of a bit weak, to be very honest. I thought it would work, but it's not really working very well. Okay, that's the way we did. And then so therefore deterministic part, the basic point I'm trying to make is the following. If we had only stochastic part, you will have a diffusion equation. If we had a component of deterministic and stochastic part comes out as the diffusion. Deterministic part comes out as the drift term. So this is what we call drift. So deterministic part in the equation of motion comes out as the drift in the how the probability density changes. That's which is also called the drift diffusion equation. Okay. Now let's come to the OU process. This is the deterministic part. This is the stochastic part. So basically, if I were to be inspired by this, we can maybe conclude in the following way. Deterministic part is this. Okay. Okay, now of course, this is basically a totally heuristic. Unless one proves mathematically, we cannot be sure. So basically, my claim is the following. So the drift part basically will come from the deterministic part in the stochastic differential equation. And the diffusion part remains the same. So this is a bit of a leap I have done because I did not want to go through the entire mathematical proof. Okay. Okay. So basic idea here is as follows. Deterministic part basically becomes the drift part of the evolution equation for the probability density, and the stochastic part translates to the diffusion part. Okay, is the sort of broad philosophy clear to everyone? What's happening here? So I'm trying to, this we derived from first principles. This again you yourself derived from first principles in the class, right? This I'm just making a bit of a jump here and saying that if you were to now again do it rigorously, you should be able to get this equation for how p changes with time. Now, why am I not doing in this class? So if you remember correctly, random walk and bias random walk, we introduced them as a discrete time process. And then while deriving this, we converted them to continuous time processes, right? But here the starting point itself is a continuous time process. And that makes the calculation slightly difficult, not impossible, but slightly difficult. Okay. So basically, if you were to do it mathematically, this is what you will find. Okay. So let me go a bit further now and generalize it. So let's take of a general additive noise. So if the equation looks like n dot is equal to f of n plus the Gaussian white noise, okay, then this equation, how does the probability density change with time, follows this equation. So as I told you, the drift part will be determined by the deterministic part, and the diffusion part will remain the same. Is that fine? So one way to see if this makes sense is, if it's a pure random walk, f will be 0, okay, and therefore this term just goes away. So if it's a case of a biased random walk, this will just be a constant, and that's where we have a constant. You get the standard diffusion equation. In a general case where the deterministic term is some rate function f, this is how the equation for the entire p looks like. Okay. So in general, this is called a Langevin equation, whereas this is called any questions before we go forward? So I understand that there's a bit of a black box here. If some of you remind me, I will be able to share the proof for this, if you want to go through the mathematical proof. Okay, no questions. Okay, now let me now tell one more useful concept, which is that the potentials that we discussed last time. Okay, now again, one effective potentials of the landscape picture. Oh, there's actually one more thing I must say in the previous slide, previous slide. Okay, this is general additive noise. What about general multiplicative noise? Okay, so which is basically the Langevin equation now looks like this: f of n is g of n eta of t. Okay, where eta is the Gaussian white noise. So what will be the? Can you guess what's the Foucault-Bank equation going to be for this? What will be the drift term? Anybody guess? So note that on the left hand side you have a time derivative, how p n of t is changing with time, whereas the right hand side is all with n derivatives. Okay, so please note it. So what will be the drift equation for this? So this is a drift term. What will be the drift for this now? New equation now.
Should be identical.
Should be same, absolutely, because that's determined. That depends only on the deterministic term. about the diffusion term? Should they depend on G? Well, obviously it does, and this is how it looks like. Okay. So this I am writing in the Ito calculus, using what is called Ito calculus. Okay, so I still haven't done what is this Ito thing. I will do it on Monday. Okay. The thing is, when we do stochastic processes, there will be some amount of technical stuff that is so inevitable. Okay, so I'm trying to minimize too many algebraic calculations, but I'm giving you some basic results here. Okay. So basically, the stochastic term Gn comes out as G square, and in fact, this D doesn't exist anymore. This D is not required. Okay, usually, I'll just tell you what happens. Okay, so when we write this in the form of eta, D basically will be replaced by sigma square by 2, where sigma is the variance of this Gaussian white noise. So sigma square by 2 here also. And therefore, we'll have the sigma square by 2 here also. Okay. Okay. So I'm just stating the results here. I have not given you any proofs, mathematical proofs, but I hope it makes intuitive sense how the deterministic and stochastic terms in the Langevin equation translate to drift and diffusion term in the Fokker-Planck equation. So remember the thing, Langevin equations are those that tells you how state variable itself changes stochastically with time, whereas Fokker-Planck equation tells you how the probability density function associated with the state variable that changes over time. Is the distinction clear? Okay. And if you had no stochasticity, Langevin equation just becomes deterministic equation, right? And the probability density function is not even required, right? Because every trajectory is identical, right? Given initial conditions. And there's another useful, theorem or a result. Okay. If I know only Langevin equation, or let us say if I know only this, there is a one-to-one mapping between, Langevin and Fokker-Planck equation, at least for one variable systems. Okay. For example, so far we have been looking at n is one single population, right? So if you look at single population stochastic dynamics, if I know Langevin equation, I uniquely know the Fokker-Planck equation. If I know the Fokker-Planck equation, I will uniquely know the Langevin equation. Okay, so they will be basically, they both sort of correspond to each other in a perfect sense. So they don't add any more information than the other. Okay, these are all some useful results to know. Now let me tell you, what do we do with this Fokker-Planck equation? What the heck will we do with this? Okay, what's the use of this? So there are two uses of Fokker-Planck equation. Okay. One is that you just solve them. So for the case of diffusion equation, you might remember that we can actually obtain an exact solution for this, right? And it looked like this 1 over square root of some pi t e power minus x squared by dt. I think there's a t here also. Okay. So we can have exact. We know exactly how probability density function evolves over time. but this solution is not always possible. So what we often do is to calculate the steady state distributions. So what does that mean? It means that we take the px of t, we wait really long, and it will reach a stage where now this probability density function doesn't change anymore. Okay, that's called the steady state distribution, and that's often very helpful. Okay, now again, without going into any of the mathematics, let me just tell you some results. Okay. So if we have an equation of this form, simple additive noise, okay, it turns out that the steady state for this follows this, this is a curly and, by the way, a normalization constant, follows this really simple form. Where u of n is think about this. So you have this Langevin equation, okay? The steady state distribution E has the form e power minus u of n by 2 sigma square, where sigma is the strength of this noise. What is u? U is the potential we learned in the previous class. Okay. Let us understand this with an example to make sense of this. Let us take the example of OV process. What is OV process? It's just this. What will be u of x for this? What's the potential for this? It's basically minus of minus alpha y dy x, and we did this last time. It will be alpha x squared by 2. Okay. Now, therefore, what will be a ps of x? I'm not going to worry about normalization constant. Okay, currently it remains same. So basically, u of x is alpha x squared by 2. So if I now replace u from this, what do I get? I get minus alpha x squared by 4 squared. How does this look like? Have you come across this function? E power minus x squared by some constant.
Normal distribution.
It's basically a normal distribution. What does it mean? It means the following, right? If you were to plot x as a function of time, it will have some stochastic behavior around 0, right? For the OU process. On the other hand, if I look at the steady state distribution, basically if I take this time series, if I just simply compute the histogram, how will this look like? It will basically be a normal distribution with more, I'm sorry for this, bad drawing, with more at 0 and with some variance that depends both on the sigma square of the system, of the external noise, and the alpha, which is the return rate of the system, right? So this is how the steady state distribution will look like. So if sigma is large, this becomes wider and wider. If sigma is small, it becomes narrower and narrower around the equilibrium. If sigma goes to 0, it becomes basically a short peak at the equilibrium at x equal to 0. So basically, the Fokker-Planck equation will tell you where will the system reside after long enough time? Does it make sense? Okay. Okay, so I think I've covered enough ground for today, but I'll just do one last result, another result. Okay, result, let's call this result A. Let's do result B. Let's consider a multiplicative noise case. Again, you can prove analytically that the steady state distribution will be of this form. Normalization, let's quickly this one, minus u of n by 2 sigma square. I may be getting this, I think I have a feeling there's those 2 here, by the way. I could be wrong about this 2. So where u of n given by this expression. Do you think u of n will depend on g? Will it depend only on f? So go back to this. U of n was dependent only on f, right? Now with the multiplicative noise, what do you think will happen? Will this depend on g? It does. How? The effective potential. So basically this is what we call effective potential. So what is interesting is that when you have a multiplicative noise, the potential of the system also depends on the multiplicative noise term. So this is the main results I wanted you to be introduced to, and this integration can be sometimes difficult to do. You'll have to rely on Mathematica or such packages, or go back to really do rigorously. So we still can't do the kind of integration you could do back. The kind of integration we did when you were in 12th. Okay. Can be quite tough. But sometimes they're also impossible to do, depending on the functional forms you have. Okay. So the basic point I want to convey with this is, there are Fokker-Planck equations are very fundamental to stochastic processes. They tell you how the probability density function changes with time. Although we cannot calculate how exactly changes with time, we often depend on the steady state distributions. This is like fixed points, it's like equilibrium of the of the dynamical systems. But here the equilibrium is in the entire probability density function itself. Okay. And what is interesting is that in the steady state, the probability distribution function depends on the potential function that we discussed last time. Okay. For the additive noise, it's a very simple potential function. For the multiplicative noise, the potential function depends both on f and g, deterministic and stochastic parts. Okay. So unless you do examples, you will not really understand any of this. Let me assure you. Okay. So what we'll do now is do some examples. That's the work for today, but I will let us restrict to a large extent via numerical example. So the lab work for today is as follows. Lab assignment 6, if I'm right. So the goal for the lab assignment is to understand the role of effect of multiplicative noise. What we know, we already know this. We have understood this very well. OU process really well. We know what the noise stochasticity that fluctuates around the equilibrium, and what you basically have with a steady state distribution is a Gaussian distribution around the deterministic equilibrium. So if you were to look at deterministic equilibrium of the system, right? What is that? That is given by alpha x equal to 0, meaning x naught is equal to 0. Basically, what we have found is that PS of x is a normal distribution around a star is equal to 0. That's what we have just formed. Does everyone agree with this? Any questions in the background to our lab assignment today? Okay. So our first lab assignment today, first part is verify this numerically. I have already uploaded the code. Plain numerical. How will you do this? Simulate whole process. Plot x versus t and histogram of x. What I also encourage you to do is the following: plot normalized histogram. I don't think you will have time for this because normalizing the histogram will require some manual work, I think. Or maybe there's a function in the R. Okay, and compare with analytical expectation. E power minus alpha x squared by 2 or 4. I think it's actually 2 sigma square. Huh? No? Not sure of prefect. 2 versus 4. So I should actually write that here also. I have a feeling there was no 2 here. I'll just write down. I'll just check and confirm later. Okay, so here's the first thing you should do today. Simulate the OU process and plot the histogram. Does it meet your expectations? Of course, you must plot this for sufficiently long time to get a good histogram. Second thing, so this is optional, okay, because I don't know if you will have enough time for this. Exactly compare, but if you want to learn better, please do it. The second part is the following. Okay, now you remember I had asked you one assignment question in the first round, which is a random walking animal with home range. Home range basically means that animals have some territory and they typically do not go beyond it. And I had asked you to come up with some, some model for this. Okay. Now let me ask you the following question: can this be a model for home range? A crude home range model. What many of you had done in the question back then was that we had put some hard boundaries. You had said that as it moves beyond a distance L, they just will turn back always towards origin. Okay, but until then they will be moving randomly. That was one way you had all modeled. But look at this. What is this doing? This is doing in a slightly more mathematical way. Basically, what's happening here is the farther you go from origin, which is the which could be thought of as home, x star is equal to 0 as the home. The farther you are from home, stronger the deterministic pull towards 0. So the home is actually modeled as a deterministic pull towards 0, and the animal is always moving randomly. Okay, so randomness is independent of where the animal is. Okay, and deterministic pull acts as a tendency to walk towards home. Okay, so I hope you agree with this interpretation, and and also it makes sense if you go back to the claim that we know that steady state distribution for this is peaked around 0, right? So it does meet the sort of basic idea of a home range. You spend maximum time at home because PS of x is at home. Okay, so now let's think of a modified model, modified home range model. Where stochasticity depends on distance from home. Now, what do you think is a reasonable form of such a stochasticity? So basically, let's now modify this. Let's now, so that is same as writing. I now have a model like this. The strength of stochasticity depends on the value of x, right? Can you now tell me qualitatively how do you think G could depend on x, whilst sort of keeping the spirit of home range? Where do you think animals are going to be more stochastic if they have a home or something like that?
Near the home.
Right. Okay, so they will be more stochastic here. What about farther off?
There will be smaller stochastic
Less
difference.
stochastic. So basically, a function that has this feature, right? Of course, there are many ways to do. You can also do this way. There are many ways to do this, right? That's fine. Does everyone agree with this? Okay. So this is how you can model where animals are, their tendency to be random also depends on the distance to home. So earlier it was constant randomness throughout, okay, which might be slightly unrealistic, right? Because farther you're probably wanting to go home and you will be less random when you are farther away from home. But here we have accounted for the difference also. Okay. Is it fine to everyone? So your assignment question is as follows now. Write some functional form you like, some g of x consistent with the above pattern. Okay. Above pattern. Okay. Then plot x versus t and histogram of x for different values of sigma. Is that fine? So for the sake of simplicity and reduce the number of parameters, assume alpha is equal to 1. Let's also assume alpha is equal to 1 here. Huh? Let's assume in your simulations, assume alpha is equal to 1. Okay. When you're simulating, assume alpha is equal to 1, but you can vary sigma and show different for different sigma and do the same thing here. Okay. Clear to everyone what you need to do? Sorry. So that's your 2 assignments today. I have already uploaded a code that simulates stochastic differential equation, and I have also told you the trick of stochastic differential equation integration, where you discretize, you have to multiply it by square root of delta t. That's all incorporated already. Okay. I think if you go to Canvas, you must be able to download the file. You must have also gotten the message that I have uploaded a code. Did you do all? So check your email in the last one. So I'm going to stop here. If you have any questions, I can answer before we go to our breakout rooms. So in today, you're not going to use any of the Fokker-Planck equation stuff. We're just going to do numerical simulations. Okay. So you just simulate the stochastic differential equations and then plot the results. And then comment on the results, of course, as always. Fine. Any questions, people? Shall I start the breakout rooms? I'll start. Assume there's a yes.